For this lesson, we will take the data that we used in the previous example for linear correlation hypothesis tests and find that regression equation. So we have that random sample of 11 statistics students where their third exam score and their final exam scores are listed. We found previously that there is a significant linear correlation between these two scores. Now that we have a significant linear correlation, we can use technology to find the line of best fit, which is also called the regression equation. The regression equation has some different notation than algebra. You may remember in algebra a linear equation is y equals mx plus b. In statistics they change some letters around, and instead of looking at mx plus b, our regression equation is going to be a plus bx. If we just switch the two terms in our algebra, in our algebraic linear equation to get the statistics one, we do just need to be really careful because the b in the statistics is not the same as the b in the algebra equation. The b in the statistics equation does not serve the same purpose as the b in the algebra equation. Sometimes you'll see a statistical linear regression equation with an apostrophe on it. We call this prime. So y prime equals a plus bx, and I'll explain why it's not just y in a moment. Our statistics book is using a hat. So y hat equals a plus bx. And the reason for this is y is representing our actual data, but y hat is representing our predicted data from the x. So x is plugged into this equation once we find a and b, which we will in a moment. We'll find a and b, and then we'll plug in an x value, and we'll get a predicted y value for that x value. That y value may or may not be equal to that final exam score. So we want to delineate between the data y and the predicted y. So this y hat is important. And now how to find it. There are several different calculations one can use to find the slope and the y-intercept. Given that we're using our technology, we can use our technology to find the averages for the x and y columns and the standard deviations. Those will allow us to calculate a and b much more straightforward than using some other calculations that are out there. A reminder from previous lessons, the slope, b, can be calculated by taking our correlation coefficient r and multiplying it by the standard deviation for the y column divided by the standard deviation for the x column. And then our y-intercept, which in this case is a, is given by the average of the y column minus b times the average x column. And these b's are the same b's. So we have to calculate the slope first, and then we use the slope to calculate the y-intercept. So we calculated our linear correlation coefficient in a previous lesson, so we're going to go ahead and grab that for this one. I'll pull up Excel. So see, we have our data here and our scatter plot. And then down below are the values that we used to run the hypothesis test. So now I'm going to calculate the mean for each column. So we'll do average and we'll do standard deviation for a sample, so stdev.s. And I'm just going to drag that formula over because I can. So we have our means up top and our standard deviations below. And like I said, I'm going to just use Excel. I have these numbers in here, no rounding needed. We're going to go for it. So B and A, B is up first. B is equal to R times standard deviation of y divided by standard deviation of x. Our b is 4.827, and a is our average of y's minus b times our average of x's. And we get negative 173.513. Okay. So let's write these down as our equation. And this is our linear regression equation for our student exam data. Now we've already determined we could predict the final exam score of a random student because we went through that hypothesis test and found that there is a significant linear correlation. Essentially what this linear equation is telling us is that if we increase our third exam score by 1 point, our final exam score is going to go up by 4.83 points on average. And we're getting that 4.83 from that slope. The slope tells us how much we change for each increment in x. If we had a student in this class that made a 68 on the third exam, we could predict the final exam by plugging in 68 for x. So calculating 4.827 times 68 plus 173.513, but make it negative, and we get 154.7. Remember that that second test is out of 200, so this seems reasonable. Also, 68 is close to 67, and we have two values for 67, 133 and 153, and the 68 seems close to it, and so that answer seems pretty reasonable. We can check our linear correlation instead of doing this work by hand. If we create our scatter plot, which we already did, there is the ability to add a trend line to the graph. Right here at the bottom on our add chart element, we can create the trend line. Or if we're in our chart tools, we've got the option for a trend line. Notice in here, if we do add chart element, there are other options. Now, notice the little arrow that pops up. I'm going to click on more options and bring up this format trend line menu, and then click all the way over to the bars and scroll down. There's some options at the bottom where we can display the equation on the chart. Excel can give us our equation, and then we can display our R² value on the chart. But the big key here is checking out that linear equation. Notice we have 4.8274x minus 173.51, which is exactly the linear that we came up with when we used the averages and the standard deviations. So we can use Excel to check our calculations, or if we're really doing this out in the real world, we would have Excel give us that equation and then use it. Being able to interpret this equation, though, for every increase that happens in x, every point value increase in x leads to approximately 4.83 points increase in y.